I tried making an experiment. So looking at the circuit, it looks pretty complicated. And I thought to myself, And then there's this other circuit that I helped Bob and Dave with making over Unity so as not to have any voltage source. And again, I use the same kind of grounding rod setup, and the other ground end is the load. Zoom in maybe. Easier to see. Here's the load. Maybe a little more. So here's one ground, up here is the load, and here's the other set of grounding rods. So I'm trying, I tried all these complications. So here's the load here, and then here's the grounding rods. What if we simplify this so that it's not so complicated? What happens? And then I did some other things. I assumed a conductive earth because those other versions, maybe I should go back to that. Like this one, for instance. This assumed a non-conductive earth here at this brown line. In other words, I'm assuming that these are all individual grounding rods that are not electrically connected except up here at the top with wire, but not down below this brown line or at the brown line. In other words, I'm assuming that all these grounding rods are set into bedrock, granite, a perfect dielectric. And of course that's not true. It's not going to happen like that. I'm also assuming a hollow earth giving me terafarad capacitance. So what if I get rid of all of those presumptions and I assume a conductive earth? That means everything gets shorted out above the earthing caps. And so my adjustment cap I have to reduce to just one from the whole assortment that I used to have up above each grounding rod. Because at this point here, the earth is going to be conductive at the surface of the earth. And so my adjusting cap is above the earth, followed by the grounding cap. And then I make it symmetrical and put the grounding cap on the other side, another one, and another adjustment cap. The only thing that makes it asymmetrical is that I have only one earth ground here, whereas I have 10 here, hooked up in parallel. Now, the way nodes work in a simulator, this looks like it's a straight line, and you line them up all in a row, 10 of them in a row, but that's not the way the simulator sees it. That's just the way it's drawn. In reality, each one of the tops, the points of the top of each grounding rod, is fused together as if it were welded at one point. So these are not, even though these are 10 separate grounding rods, these red dots represent a single dot from the simulator's point of view, in which all of these 10 grounding rods come together at a single junction point. And there's no stipulation here as to how far apart these are. Here, they're no distance apart because this is the conductive earth. So now we're assuming that the oh, this is weird. What are we assuming? Do we have only one rod and it meets up with bedrock? And these across the planet are 10 randomly sized, randomly placed pockets of bedrock separated by what? More bedrock? Or are these 10 planet Earths that we're grounding ourselves to? You see, I don't even know. I don't even know what this circuit represents. This could be 10 planet Earths right here. What do I know, you know? Because it's really weird how this thing, I cannot shut it off. I cannot shut it off. And I can't, even if I eliminate 9 of these, and just leave 1, I still can't shut it off. Because all I have to do is run it long enough and it'll blow up. That's what's so uncanny about it, is that if you run it long enough, anything you try to do to shut it off will not shut it off, other than maybe putting a switch up here maybe will shut it off. I don't know, but you'll still get a... Well, maybe I didn't try that. Maybe I should try that. I don't know what I'm doing anymore. Alright, so I'll just show you. I'll run it. And since I ran it for 34,000 seconds, there's this nice buildup right here prior to 7,000 seconds. So let's say that's actually 5,000. So at 5,000 seconds, it reaches its plateau, more or less, of 7.5 times 10 to the power of 128, which is a lot of wattage on the inductive load. That would be this thing here. So let's put and make believe this is a switch and take that out, and then we do it. Matrix is singular, so it doesn't like it. So let's go find out what happened, because I'm not going to run it at a different time frame, because it's always best to run these as long a time frame as is possible. You get much more accurate results that way. Let's see if it comes out of hiding. No. Okay. Alright, let's try 1 microsecond. Uh-oh, this is not good. Well, I've never done this before, that's why. I don't know what I'm doing. Interesting. It doesn't like it. What if we take out the other one? It doesn't like that either. How am I supposed to find out how this thing runs? I wish I had practiced this before making the video. I keep thinking of new things. Don't complain. Oh no, this is horrible. Oh, there we go. So we're getting a lot of impedance, both positive and negative triangle waves. The power is rising. See, even though it's negative, the power is rising. So there's no guarantee it's not going to blow up if you take it far enough. I said that, didn't I? So let's try e to the 1. Ah, see, it's growing. The negative impedance is growing. That's not a good sign. Well, no, it alternates, but it's triangle waves. That's not a good sign. Let's try 2. Ah, see? Now it's picking up. The energy level is picking up. So if you run this long enough, it explodes no matter what you do. The wattage is still 0 on the inductive load, but that kind of makes sense because it's not... It terminates... It doesn't even ground itself. And that's probably why it can't compute it beyond a certain point. It doesn't like a circuit that's... Oh. The wattage is still 0, but it's it's dissipating a humongous amount of power. You see, this is what's so bizarre about this circuit. It is just so bizarre, it's impossible to try to figure it out, you know? It's just really bizarre. Now, this is at a lower value of time, and so it doesn't behave very nicely. The circuit, or the simulator, doesn't like too short a period of time, so this one works best, or anything greater, 34,000 seconds, or more or less, or more, by powers of 10. Anywho, oh gosh, So that's the circuit, the power. Now the current was really weird. Let's see. So all the current is coming in through the 10 grounding rods, and then it's going out from the load. Well, not really, through the singular grounding rod, because it goes in reverse on the other side of this adjustment cap. It's going towards the load. So it's a little weird. Here's the nodal voltages. They're very extreme on the top side of the adjustment cap here, and on the top side of this adjustment cap over here, because this is the same value. Oh, I can't light it up. Forget, this is not the simulator. Let's see. Oh yeah, that's the output, you saw that. So, you know, it's really bizarre, but that's what I got to tell you. Not much. Well, I did figure out what I was having trouble figuring out. With the help of Bob French, who spoke to me last night, and with the help of Jeff Goldblum, who came to me in a dream. So we'll start with Bob. He suggested that I loop this set of grounding rods to this one and just, you know, reduce everything down to one grounding rod, and that's what I did here. And so he also, as I was talking with him, he helped me think through the inconsistencies that I was seeing, that why I call this weird, because I couldn't understand what these 10 grounding rods were representing. And then I realized, no, wait a minute, I have the conductive earth at the wrong place. I had it up here at the top of the 10 grounding rods that were fused or welded together at their top. And instead I realized, no, it's at the bottom. And these are not earth caps, these are just whatever caps you want to use, because then I started playing with it further, and I was able to reduce it to just about any ridiculous amount. I mean, it's ridiculous. It almost doesn't matter how much they are. But it does matter. The more they are, the more stable the circuit is able to simulate. So, you know, more stable outcome. So he looked online for non-polarized, non-electrolytic capacitors, and he found 1.5 millifarads was the largest he could find. So then I just made 10 capacitors that are connected in parallel with solder joints of 2 milliohms of resistance per solder joint. 10 capacitors called earth caps, and each one is 1.5 millifarads, and each one is charged with 1 microvolt from the environment, because they're situated right below them is the conductive earth joining them together, and there's a piece of wire, or they're welded together or soldered together. Actually, they're welded together. Well, no, they're soldered. Yeah, they're soldered together at the top, they're soldered together at the bottom, and then they go to a grounding rod, and so in between these 10 and the grounding rod is the conductive earth, representing the fact that they're all fused together, but they're also fused together with wire. Well, they're fused together with wire down at the bottom, but it's congruent with the surface of the earth, which is also conductive. And assuming the earth is not contributing any resistance, because anyway, I should have put this line below this junction is what I should have done. Whatever. I put it where I put it, so I'm not going to change it. Yeah, it's a little misleading, because actually, well, it's not that misleading. I don't know. Anyway, what else did I do? Oh yeah, I managed to put in 2 resistors here, so now these 2 coils are separated from each other. And these coils have to be less than these coils in order to function. If you make these coils the same inductance as these 2 coils, then the whole thing goes flat, comatose. And I tried doubling them, as too much, so they have to be 1/10 or less each one than each inductance of these 2 coils. Now these 4 coils are not necessary. You could put any load here you want to. And these 2 coils are basically connected to themselves, isolated from the rest of the circuit, electrically isolated, but magnetically coupled, which means they're wrapped on top of these 2 coils that are connected together. And probably this is a toroidal form, although I don't know, maybe it's a solenoid core. But see, these 4 coils, I had to simulate them as air core coils. So I don't know how they would behave with iron core. Not that I think it would make much difference. Well, it might ease up the explosive nature of this circuit. It's so explosive. Let's see what else. Oh, and it doesn't matter what the inductance is. The coupling between these 2 coils and the 2 coils they piggyback on top of it, you can make it 0.00001, just so long as they're coupled. It's really bizarre. So you could have it waving way out here. It's really bizarre. Some things do matter because they increase stability. And actually, the magnetic coupling between these 2 coils on the right and these 2 coils on the left, the higher the coupling, the more efficient, the more rapid is the acceleration towards infinite gain. So things do matter, but they don't matter in terms of functionality. They only matter in terms of efficiency. But in some cases, it does matter in terms of functionality. So, but I mean, there's wiggle room, basically. So the ground cap and the adjustment cap are both picofarad each. They're both 1 picofarad. Now, Jeff came to me in a dream. We were on a rounding course up in Ramona, a residence course, TM, Extra Meditations. And he indicated to me that I needed to short out from the circuit to ground through an air sparking gap. And the minute he said that, I said, oh, quick. This was in the dream. Oh, just a second. I got to write this down in my notes. And then he got disinterested in me because it was obvious I felt the desire to share with other people, but I knew before I went to sleep that it was his and other people's feelings that I don't need to share anything with anyone. So, once I made that decision, he got up from the table, and because we were sitting at the table, and he turned and looked at other things and, distracted himself because he wasn't interested in me anymore, because I obviously wasn't interested in what we came there to do, is to become enlightened, and I wasn't interested. I just wanted to share new knowledge with other people. Must be my ego, my guilt complex. So I didn't remember it right away. As I was laying there in bed after waking up from the dream, I had to think a bit about other things, and then I thought about Jeff Goldblum, and I thought, oh, I dreamt about him. What did I dream? And then I remembered the dream. So I thought, oh, I might as well, I never did post this video, so I might as well add on more stuff and then post it. So this is what I did. I did a voltage, I looked at the nodal voltages. Let's see if we can find it. No, here. So I looked at the nodal voltages, and they tended to be very high on either side of say, I had only one resistor here at the time. They was very high around this resistor and very high between this resistor and this resistor. It was like 66, e to the 66. So then I decided, well, why don't I put a switch in both places? No, excuse me, a connection to ground, and through the ground I first have to go through a sparking air gap, not a neon bulb, but a sparking air gap with 1,000 volts of breakdown voltage as its threshold for breakdown voltage. And I tried different positions. I tried both. The circuit went comatose. Then I tried one up here and one down here. And regardless whether I put one up here or one down here, the time for reaching the limit of what the simulator could handle before it crapped out on me, e to the some ridiculous power, shortened. And it was 4,000 in one instance, 4,000 seconds, and it was 2,000 seconds or thereabouts in the other instance. So I thought, well, 2,000 is better than 4,000, and you don't have to wait so long. So this is the arrangement I chose. So GR goes to this grounding. So I put a resistor on either side so that I could protect the volt, so I could see the voltage on either side. It doesn't really protect it because these are small solder joints, SJ for solder joints. But then I could get a voltage reading and see how it's doing on either side. And so this always goes to ground. And when the voltage builds up enough, this flares, this arcs, turns on, and then it accelerates the growth. so that instead of waiting 40,000 seconds, you only have to wait 2,000 seconds. But then I had to leave this one open in order to run the thing. But if you close this switch to engage this also connecting to here, then the thing goes comatose. It shuts off. So this is the on-off switch. When this switch is open, the circuit is on. When this switch is closed, this circuit is off. The over-unity goes comatose because everything grounds out to the earth through this sparking gap in two places rather than one, here and here, and the whole thing goes comatose. So this is the schematic. What else? Did I change anything else? No, I think that's it. So now these were the dissipation and storage values. They were all in the tera around the coils here, giga and mega around these coils here, mega and tera around these, I want to say Cabbage Patch Dolls. No, these capacitors here. Oh, e to the 25. So it's very high over here on this adjustment cap. E to the 25 on this one. So between this grounding cap and this adjustment cap in this whole range here, with this switch open, we've got e to the 25, 10 to the power of 25 stored power, while the dissipated power is terawatts. The stored power is wattage of 10 to the power of 25. Down over here it's pico and femto because it's adjacent to the ground here. It's shorted out to the ground. So it's nice and small. And then we got a ground here that's engaged too. So there's no reason for this section of the circuit to be high. It's very low. This is the only part of the circuit that's low. Then here right away it's up to e to the 24 again on this side of this grounding cap. And then it drops down to mega before it goes up to tera around these coils. So let's go to the next next screenshot. Oh yeah, so here's the output in the numbers. So the value of numbers, negative watts down here. Well, let's go to the next one. Well, yeah, whoopsie, we saw this already. Here we go. So the wattage of all four coils, the two that were up here, the smaller ones that are looped to themselves and electrically isolated from the other two over here, all four coils, the total combined wattage is negative watts, and the circuit terminates at e to the power of 41, which is less than what it did before without these grounding shorts. It went all the way to like e to the, I don't know, 240. It can go as high as 290 something. Before it craps out, but in this case it crapped out at an earlier point in time, which doesn't mean it couldn't go any higher. It just means it crapped out at an earlier point in time. But because it accelerates over time, it wouldn't take much longer than, oh no, it's actually 3,000 seconds for it to reach e to the 200 or e to the 300 for that matter, if your circuit could last that long, because it escalates as it grows. It accelerates. It doesn't keep the same rate of growth. Unfortunately, you can see how vertical this is. Now these are hyperbolic, so it's nice and smooth. This is the power, excuse me, this is the energy storage, and this is the energy dissipated. And the energy stored is greater by a factor of 1,000 than the energy which is dissipated. So the storage is in the caps and coils, and the dissipation is through resistors. I don't have any diodes, so it would be resistors. Now the time interval, it starts out very high, and it's in the negative. Uh-oh. This is wrong. I'm going to have to change this. Because it starts out, oh, here it's positive. Right, the dissipation starts out being positive, and then it goes to nearly zero. But here it starts out negative. The power stored. So it shows that the caps and coils are generating power. Now the load is negative. it rises, and it has a negative spike of negative impedance around 2,000 seconds. So let's go back to the numbers. So let's see. It doesn't show that here. Probably because it was at the wrong point. I didn't go all the way to 0. Yeah, but the graph shows that it's negative 1.2 e to the 29, the stored energy, the total stored energy. So it does spend a little time in the beginning, negative watts, but then it becomes positive and very small. It stays at around 100 millisecond time interval, positive. So 1/10 of a second, positive time interval. So most of the time, it's running time forward. It's just in the very beginning that it's time going in reverse in the caps and coils. In all of the caps and coils, it's only the loads that are entirely negative all the time. That's what it looks like, because they're negative in the beginning. E to the negative 150, negative 4 times e to the negative 150, and then at the end, negative 1.5 times e to the 41. So it's always negative in the load areas. So that would be, here, these two coils, and here, these two coils. Oh, maybe I was showing you the wrong nodal voltages. Oh, so this is the correct nodal voltages. I'm sorry. So let's see. Right. Yeah, what was that one? Oh no, I don't know what. Oh, I don't know. Whatever. Current. So let's see which way. The current is running around in a circle here, and it's going through these two in the same direction towards this ground spot, because it's all going to leave through this ground. So it's coming in this way, and this way, that way. Now it's going this way here, but it's going this way here. So this section in here is like high voltage, and it's leaving in both directions. So it goes down through these parallel capacitances to the earth, obviously. So everything all the current wants to leave and go to the earth. So that's normal. Oh, that's everything I had to say. So we'll show you the grounding. So, excuse me, grounding, right. You ground yourself to this download link to get the files. It has the screenshot files and the simulation files. There it is. And I guess that's everything I've got to say. So isn't that superb? I love it. I love this new circuit. Thank you, Jeff, and thank you, Bob French, and thank you, Dave Bowling, for listening to me, making me feel wanted and needed.